Hi everybody, this is your video on inverse functions. It's an introduction to them to get ready to work with logarithms more and learn different ways of solving. So before I actually talk about inverse functions, I want to take just one more second to clarify inverses, reciprocals, and opposites. They are three of the most commonly confused and mixed up words in math. And whenever I was grading the quizzes, I noticed that people were mixing them up as well. Now, opposite is the one you learned first. When you say numbers are opposite, that would be like opposite in sign. Most likely like 2 and -2 are opposites. When you say reciprocal, some of you are mixing up reciprocal and inverses. So a lot of you on the quiz were saying like 2 and 1/2 are inverses of one another. You have to be careful whenever you say that because 2 and 1/2 are better described as reciprocals of one another. Just like 3/2 and 2/3 are reciprocals of one another. If you're going to say that 2 and 1/2 are inverses, you really need to clarify multiplicative inverses. They're not inverse functions. So inverse functions is something different. Inverse functions are functions that are going to undo each other. And we're going to start with functions that you're more familiar with that are inverses of one another. So usually if you're looking at a book, they're going to say f and g for the inverse functions. And let's take a set of inverse functions that you're very familiar with. Let's do x squared and the square root of x. So take a minute and pause the video and get a table and a graph set up here so that whenever I do it, you're caught up with me. So let's let f of x equal x squared. And let's let g of x equal square root of x. And I realize that you've thought about this stuff before in terms of undoing each other, but I just want to demonstrate it one more time with the number 4 so that when we do it with logarithms, it's more intuitive for you. So let's let our input be x equals 4. So if I have 4 and I square it, so I apply f of x, and then I do the square root of it, so then I apply g of x, I'm going to end up with 4 again. Similarly, if I take my input of 4, and this time I do the square root of it first, so I do g first, and then I square it, so I do f second this time, I'm going to end up with 4 again. So it's really important that you realize inverse functions undo each other, or another way of saying it is they cancel out each other's operations. So whatever one does, the other will immediately cancel out the effect of it. All right, so we're going to graph f and g on one grid together, and we're going to notice as many things as we can about these inverse functions, because the things we notice are going to hold true for all inverse functions, including logarithms and exponentials. So I'm going to do x squared in blue and square root of x in green. So let's go ahead and get some inputs and outputs here. I'm picking these inputs strategically because I don't feel like plotting decimals or fractions. So this is really quick to fill out. So 0 squared, 1 squared, 2 squared, 3 squared, and then square root of 0, square root of 1, square root of 4, and square root of 9. All right, so take a second and plot these points and make a smooth curve, and then I will unpause this when I do it. So hopefully your graph looks something like this. And I want you to, hopefully you notice that whenever you did the tables, these tables are basically the exact same thing, except whatever x was here, it became y, and whatever y was here, it became x. So one thing that we should notice here is that for inverse functions, the ordered pairs are switched. So I'll write this down here. Ordered pairs are switched. So anything that was an xy now becomes a yx. All right, now I want you to look at the graph carefully. And you did this on a piece of paper, so hopefully you can see that they are basically the same shape, just tilted differently, and hopefully you can realize that they are reflections of one another. I want you to think, how would you fold your paper or move it so that whenever you fold it, that they lay on top of one another? Like, what is the line of reflection? It's not going to be the y-axis or the x-axis. And if you look at this, hopefully you can see that if you were to fold the paper diagonally, like right along here, the green graph would lay on top of the blue graph. And you can actually try folding your paper to see it. And then the question is, all right, well, what exact line is that? And if you were to graph that, that is the line y equals x, the one that goes right through here. Y-intercept is 0, slope of 1. So inverse functions are reflections of one another over the line y equals x. So get that jotted down. Okay, so those are things that are going to hold true for all inverse functions. And let's go ahead and apply that to logarithms and exponentials, because logarithms and exponentials are inverses of one another. And we're going to graph it and get some points here just so you can see exactly why and how they are inverses. Okay, so one thing to realize is if I have an exponential function b to the x, then its inverse will be log base b of x. So whatever the base of the exponential is, that's going to be the same base as the logarithm. If the base is not the same, they're not going to be inverses. So what that means is, let's write some examples of inverse functions so you get the hang of this. If I have an exponential 6 to the x, what would the inverse be? So it's going to be a logarithm. The base is going to be the same. Log base 6 of x. What if I have e to the x? That's a very common exponential function with modeling. What would the inverse be? Well, it's going to be a logarithm with the same base. So, okay, I'm not going to write log base e. I'm going to write natural log of x. Another one to make sure you're okay with, if I have 10 to the x, what would the inverse be? That would be log base 10. I don't even have to write the base if it's base 10 because it's the common log. So let's take the pair 2 to the x and log base 2 of x. And what we're going to do is get some points. We're going to plot them and we're going to notice things. So go ahead and fill out this table with me. All right, so what I want you to do is get this set up here. And I want you to pause the video, fill out both tables. Then I want you to fill out both of these chunks of information, one time for 2 to the x and one time for log base 2 of x. Do it after you graph, obviously. You should notice the same thing we noticed above with the tables and the graph. And then once you're all done with graphing and filling out all the information, then I want you to unpause and check. Now, it's important that you do this on your own so that you can see what's going to happen. No calculators when you do this.
Time to take a look.
All right, so you should have the following here. Make sure your tables are good, make sure your graphs are good, and hopefully you realize that these are definitely reflections over the line y equals x. They're perfect mirror images of one another over this line. Whatever x was here, y was here. Whatever x was here, y was there. Whatever y was there, x was there. So the domain, range, asymptotes, and intercepts are really important. So let's check how you did on those. The domain for an exponential, it goes left forever and right forever. That would be negative infinity to infinity, or you could have said all real numbers. The range for an exponential, it doesn't go below the x-axis. The smallest value it gets close to but doesn't reach is 0. I'm going to use parentheses there, to infinity. The asymptote for the exponential is y equals 0. And I'm going to make sure I have that plotted. And the intercept, it only has a y-intercept of 0, 1. It does not have an x-intercept. All right, check your information for the green or the logarithm one. All right, domain here, it does not go left forever. The smallest x value it gets close to is 0 without reaching it. It goes right forever though, so that'd be infinity. It goes down forever and slowly goes up forever. There is not a horizontal asymptote there. Sometimes people think a logarithm has a horizontal asymptote because it looks like it's leveling off. It's going to keep growing super slowly. Logarithmic growth is one of the slowest growths there is. So the range does go up to infinity. The asymptote here, let's see, we actually have a vertical asymptote. Now remember how I said x and y switch. That means if the exponential has an asymptote y equals 0, its inverse will have an asymptote x equals 0. It's right here. Make sure you plotted this. It's very important. It has an x-intercept of 1, 0. There's no y-intercept because it never touches the y-axis. Last thing I want to talk about is end behavior here. So this is something you'll talk more about in pre-calculus. It's also a calculus topic because it has to do with limits. We're not going to go full force with limit notation here, but just good things to notice here. If I'm on 2 to the x here, so put your pen or pencil on 2 to the x and follow it. As x goes to infinity, so as I go to the right forever, what do the y values do? So as x goes to infinity, the y values also go to infinity because it goes up, up, up. As x goes towards negative infinity, let's put our pen or pencil back on the graph and follow it. As our x's go left forever, what do the y's do? They're clearly leveling off. They're tending towards 0. Now let's do log base 2 of x. So this time as x goes to infinity, so let's get on our graph here and follow it. As our x's go right forever, what are the y's doing? Well, they're slowly going towards infinity. And as our x's go to negative infinity, careful here, I can't even go to negative infinity because I can't go left forever. The farthest left that I can go is 0. So I'm going to change this as x goes to 0. Y goes to, so I'm hitting up against a wall basically here. My y values shoot down to negative infinity. All right, cool. So now that we know that stuff, we can state 2 properties of logarithms and exponents. The 2 inverse properties that we can state are the following. Now, when I write these down, I don't want you to freak out and think, what the heck is that? Because we're going to plug numbers in and then it'll make sense. If I have a base of an exponential, b, and the exponent is a logarithm itself with base b, what we're going to end up with is just x. Similarly, if I have a logarithm, base b, and the argument of the logarithm is an exponential of base b to the x, I'm going to end up with x. So I realize that this looks a little bit strange, but let's put numbers in, and it should make sense here. So we're going to let b equal 5. So let's rewrite this so it looks a little bit nicer. That would be 5 to the log base 5 of x equals x. Let's see if this is true. Let's try plugging in an x value. Let's try plugging in 25. So I'm going to plug 25 in here, and let's see if we get 25 back, because that would mean that this statement is true. So I'm going to do 5 to the log base 5 of 25. Okay, so let's think about this. What is log base 5 of 25? Well, the power 5 needs to get to 25 is 2. So now I'm left with 5 squared, which is, oh my gosh, 25, hooray, so it's true. Basically, if an exponential and a logarithm cancel completely, you're left with whatever the argument of the logarithm was, so x. Next one, let's try, I want to let b be 6 this time. So let's rewrite this here. That would now say log base 6 of 6 to the x. Let's see if it is actually x. This time, let's let x equal 2. And let's see if this makes sense. Log base 6 of 6 to the second power, does it equal 2? Let's start on the inside here. 6 squared is 36. And is log base 6 of 36 2? Well, what power does 6 need to get to 36? It is, in fact, 2. So both of these, hopefully now that you saw that, it makes a little more sense. Just like on this one here, the canceling, we have canceling here. If I have log base b and the same base b to the x, they cancel, leaving you with x. And the x is no longer an exponent. So that being said, I have a couple for you I want you to try. So here are your 6 U tries. They're relatively quick, and you're going to be using these 2 properties above that we just listed. Just as a quick demo, these are very quick. All you're going to be doing is saying, okay, let's say I have log base 5 of 5 to the x plus 1. Bam, those cancel because the bases are the same. I'm left with just x plus 1. So try these. A couple of them are going to need some manipulation first. in order to make this base and this base the same, for example. All right, I'll see you in class. Bye.